This portion of the lecture is going to be the introductory part on ethers, and we're going to talk about nomenclature and some preparations of ethers in this part of the lecture. The ethers are the molecules that contain compounds that have an oxygen in between two carbons that are not carbonyls. So the carbons can either be sp3 hybridized or sp2 hybridized as part of an aromatic ring, for example, or an alkene, but they can't be double bonded to an oxygen. That's what a carbonyl is, because that would be a different functional group. So we have some examples here. It doesn't matter what degree the carbon is either. So if you have just plain old alkyl sp3 type carbons on either side of the oxygen, then we can just name it in kind of a different way than what we've seen before. So we're going to think of this group. So there's a methyl group, and this, you see the branching is here, that's an isopropyl group. And so you could just write those down, skip a space, and put them in alphabetical order, and just lay out those three words, and that would be the name of that ether, isopropyl methyl ether. You notice in this case that the alphabetization used the non-standard prefix for the purposes of putting it in order, and whichever order you put it in is incredibly critical, because remember, the purpose of the nomenclature is to just make sure it's clear. We haven't dealt with aromatics yet, but they do have an example here. When you have a benzene ring by itself, that's a phenyl group. And so they give you this example because in the placement of the book, they've already done aromatics. I probably wouldn't ask you that at this point. But again, there's an ethyl group and we have a phenyl group, putting them in alphabetical order, skip a space between the words, and you have ethyl phenyl ether. Sometimes you'll hear people use the word ether and not write anything more definitive, or in the book as a solvent, for example, they might just put ether, and when they do that, this is the one they mean diethyl ether. It's the most common ether, and so it's just two ethyls, and so we can condense that together rather than saying ethyl, we just put the prefix di, that we have the same two things on either side of the oxygen. There are some common names for some ethers, so here's an example, and the methylphenyl ether's common name is anisole, and again, I don't really think you need to know that, especially not right now. There's another way of doing this. Sometimes the ether is a fairly small part of the whole molecule, and or you need to number, and so if the oxygen is the only functional group present, then you're going to sort of take that as your reference point and number away from there. So this carbon chain is numbered starting at the carbon that's attached to the oxygen, and so we have a 3-methyl, and that's a 4-carbon butyl group. And so this part of this name comes from there, and then we've also had a numbering system, again, starting at the oxygen carbon bond there, that's number 1, and so we could name that as 1'-methyl ether, methyl ethyl ether, for that portion, or we could call that an isopropyl group. So either one of these two names would be acceptable. We also have a lot of cyclic ethers, and you should know these. This is tetrahydrofuran, and it's a 5-membered ring, and the oxygen is one of the members of the ring. It's abbreviated THF. And again, that's a very common solvent that you'll see used in lab or in the book. That's the molecule that they mean when they say THF. 1,4-dioxane is another cyclic ether. It's got the two oxygens in the total 6-membered ring, but they're on opposite sides. So you could have 1,2, that's a slightly different functional group, or 1,3. But those are not as common. This one is used as a solvent. And then we have these really big molecules, this 18 crown 6, and it looks like a crown kind of, and I have a couple of other pictures for such a thing. This one is 15 crown 5. The way these things are named is by the total number of atoms in the ring. And so there's 15 atoms in this ring, and then it's called a crown, and 5 because 5 of the members of the ring are oxygens. and so that's where that name comes from. So here's just two different views of that. You notice the way that it's oriented in this picture and the previous picture is that all the oxygens are inside of it, and we'll talk a little bit more about the characteristics of that later. So if the ether is a group on a larger chain, then we might want to name it a different way, letting something else be the primary functional group. And so here's one way to do that. So this is a benzene ring, and again, we haven't had this kind of nomenclature yet, but they're using this as a methoxy group, so there's two of them, so there's dimethoxy on there. And again, I'm not going to ask you to be able to name aromatics, but I do want you to see this example of how you deal with the ether as a group when it's just a small part of a bigger molecule. This one looks a little bit more reasonable. This is a T-butyl group, a T-butyl group and an oxygen, and then you have this alkene. So you're trying to decide, how do you name this? And one thing you can do is you can say, well, okay, I'll treat this cycloalkene as kind of the parent, and then let this be a group off of that. So the way you name alkenes is you number through the double bond and give it as small numbers as you can. And so then that puts this oxygen group over here at carbon number 4. And so that's a tertiary butyl group. And so since the oxygen is part of it, then we put the OXY suffix on there. So that's a 4-T-butoxy or tert-butoxy group on one cyclohexene. And really the 1 here is kind of optional, because then if you say cyclohexene that how you've numbered it. But if you put the 1, that's okay. So make sure that you understand that OXY suffix means that there's an oxygen before the root word for the number of carbons. So this oxygen that's present in these ethers is going to make these guys be a little bit more polar than just a chain of alkanes, and that's going to increase the attractive properties between the chains, but only a little. So if you compare similar molecular weights compounds, the dimethoxy ether is similar in molecular weight to propane. It just is, a CH2 has a mass of 14 and oxygen has a mass of 16. So this is just 2 molecular weight units higher than in molecular weight than propane. And it has a higher boiling point because of the polarity of these bonds right around this oxygen. So that increases the dipole-dipole interactions, and so the attractive forces are a little greater. And you'll see similarly, you compare diethyl ether to pentane, and again, the boiling point is pretty similar, and so the oxygen is getting to be less of a component here. If you compare the THF to cyclopentane, you see a bigger difference again, because the oxygen is, these guys are pinned back out of the way, so you've got a lot more polar bond in there. And here's a higher boiling point, again, similar boiling. So generally, you see higher boiling points for similar molecular weight molecules that contain an oxygen versus no oxygen. The increased polarity causes a slight increase in the boiling point, as long as the oxygen is playing a big role in the molecule. If you have a really long chain of carbons and there happens to be an oxygen in there, it's not going to have that much of an impact. In terms of the bond angles, when you have this oxygen, it's technically sp3 hybridized, so the bond angle is supposed to be 109.5, and you see a slight deviation from that because of the unshared pairs of electrons are kind of distorting that angle, but it's still a lot closer to 109.5 than that gives you credence to the idea that it is an sp3 hybridized oxygen. And the little guys are going to be fairly soluble in water, at least more soluble in water than a similar molecular weight alkane would be. So in terms of making ethers, we know some things that we can use to help us. Um, there's an industrial route that's actually a type of dehydration, and because it's a type of dehydration and it's going to go through an E1 elimination, and so that means that it, it, it would be in competition, sorry, with some other things. And so if you do this as industrially, it works really well to make diethyl ether, which I told you is the most common kind of ether. And so here's a mechanism. Your alcohol gets protonated, and then the other alcohol molecule does a substitution reaction. And if, I think I misspoke up here, the competition is if the other choice would be elimination. And so if you had a branchier alcohol, that's when you'd start seeing elimination, which is something that we talked about earlier. The confusing thing about this really is that we're going to see this done mostly with sulfuric acid as the acid here. And we've already used sulfuric acid to dehydrate, which is the elimination. And that doesn't work as well because it's E1 on ethanol. And so this substitution is actually favored on the primary alcohol. But one way that you can make it work is you can remove this ether. And think about it. The boiling point of the ether, we saw it on an earlier slide, was in like around 30-ish, or pretty low, and it's pretty volatile. And alcohol, because of hydrogen bonding, has a much higher boiling point. And of course, the water and everything is much higher boiling point. So if you put these guys together, then as this forms, you can let it boil out, and so you can kind of pull the reaction along that way without having to heat it up very much because it's so low boiling. If you heated it up, remember, heating favors elimination. So if we want the substitution to occur, we don't want to heat this up. And so, all right, so the bottom line here is this is an industrial route, so the chemical engineers can really control the process and fine-tune it for what they want to come out. Even though they're using sulfuric acid for a number of different things, they can control how it's going to come out. But if you were trying to do this in a lab, it would be a little tricky, so we really need some other ways to do such a thing that isn't quite so subject to so many different outcomes. So there was a guy named Williamson who came up with this way of making ethers using an SN2 reaction, but instead of just taking two alcohols, he is going to take one alcohol and let it be the nucleophile on the other, and the other guy is going to be the substrate, and we're going to use an alkyl halide for that. And this is the kind of reaction that we talked about in chapter 11. It's an SN2 reaction. So here's an example. If we have this alcohol, and when we put in a base with an alcohol, we can make a salt out of it, just like we could with water and sodium metal or sodium hydride. We can make an anion out of that alcohol, and now it's going to be a better nucleophile. And now here's our substrate. In this case, the iodine is the leaving group. So we do the SN2 reaction on the methyl group, and the iodine leaves. And so the other thing that's not written out here is sodium ions and iodide ions. And so you get a pretty good yield of this ether. Now, when you look at this molecule, okay, and you start thinking about, okay, if I needed to make this alcohol, how would I know which side is going to be the alcohol originally and which side is going to be the alkyl halide? So you want the less crowded side to have been the substrate, which means it was the alkyl halide. So this is the less crowded side. This one is quote-unquote 0 degree. This one is secondary. So you let the less crowded side be the substrate for the SN2 step. So let's make it sort of a generic example. So we have an alcohol, and we react it with sodium or sodium hydride to make it into an alkoxide anion. And then we take that alkoxide anion and react it with a substrate, an alkyl halide that's not too crowded right here at the carbon that's going to undergo the reaction. And so we can make our ether that way, and we have these other products that we don't care about. Or we can sort of condense all this down. We say we take the alcohol, and in the first reaction, we treat it with the base to make it into an anion. So that's what we're doing right there. And then in the second reaction, we put in the substrate, and we do the SN2 reaction. So this is just a condensed way of writing these two reactions. So let's take an example. Suppose you have this ether. And again, we're going to think about this in terms of which piece of this is going to have been the alcohol and which piece of it is going to have been the substrate for the SN2 step. And we see that the substrate for the SN2, we know that it has to be less crowded. We learned that in chapter 11. So we're looking at the degrees of the carbons that are directly attached to this oxygen. So this guy is tertiary and this guy is primary. So which one is less crowded? The less crowded one has to be the one that is the alkyl halide. In other words, we're going to make this bond. All right? And so that means all of this has to have been the alcohol that we take through this process up here. And then we add this guy attached to some halogen. That's going to be the substrate. So here's how we write that. We have the tertiary carbon attached to the alcohol. So that's our alcohol. We treat it with the base to make this into an anion, and then it's the nucleophile on this primary carbon, and we lose this, and that's the best way to make this ether. Let's try that again. Suppose we have this ether. Now, we don't know very much about aromatic rings yet, but I will tell you that aromatic rings, these carbons can't undergo SN2 reactions. I know we haven't studied them yet, but they can't flip. Remember, SN2 reactions do inversion of configuration. This carbon can't do that. This carbon is primary. So what we're seeing here is that it looks like this piece over here needs to be the substrate, and we need this part to have been the alcohol. So this is the bond that we're going to make right here. And so we need this alcohol, and it's a phenol. React that with the base. We'll make the anion right here, and then that's going to be the nucleophile for this SN2 step. Now, in chapter 11, we talked a lot about competition between substitution and elimination. So let's just go back to that example that we had earlier, or something similar to the reaction we had earlier. If we take this guy as the anion and use this as a substrate, we can get our ether that we want just fine, because this guy's not too crowded, and so it makes a good substrate for the SN2 process. What if we went the other way? What if, so here they've redrawn the T-butyl group and they just kind of fluffed this out. So instead, if we try to let this side be the alkyl halide and the other side be the alcohol, then it could cause elimination, and that's an E2 process, to get a double bond. Remember, every time you make a double bond, that's elimination. And so you would just make this guy pick up a proton, so it would become an alcohol and you get this alkene. So that's what we mean when we say elimination is competing with substitution. If you pick the wrong side to be the substrate, if it's too crowded, it'll just make alkenes. So that's how we know and why we have to choose the less crowded side to be the substrate. Now that's all well and good as long as one side or the other isn't crowded and you can do an SN2 reaction. But what would happen if both sides of the ether that you're trying to make are crowded, and so they can't do an SN2 on either side? So we're going to talk next about reviewing a reaction that we've seen earlier to make alkenes into alcohols. That was called oxymercuration. And we're going to take that reaction and we're going to review it, and then we're going to look at how we might modify the reaction conditions a little bit in order to make ethers. And I'm going to stop these slides right here.